In calculus of residues, we have discussed in detail the calculation of residues of an analytic function at its isolated singular points. Now today we are going to utilize this concept of calculation of residues in finding the integral of an analytic function at some of its singular points, but this is done by using a very important theorem which is known as Cauchy Residue Theorem. So first of all, to solve such problems, we will discuss in detail the Cauchy Residue Theorem, and after that we will see how this theorem is used in finding the integral of an analytic function at some of its isolated singular points in case of the variables which is either a complex variable or a real variable. So first of all, let us see what is Cauchy Residue Theorem and then how it will be utilized in solving such problems. So the Cauchy Residue Theorem, I have mentioned here the statement of the theorem for your convenience. The theorem states that if the function f of z is analytic inside and on a simple closed curve, let us say C, except at finite number of isolated singular points within C, then integral of f of z along C taken in anti-clockwise sense is equal to 2 pi I into sum of the residues of f of z at all singular points inside C. Let us see here, the statement says we have to take only the residues at those singular points which are inside the closed curve C, not outside of it. In problem we will see there will be some singular point which will be outside of this region, but we have not to evaluate residues for finding this integral at those points which are actually outside of the closed curve C. Or in other words, you can say this integral of f of z along C is equal to 2 pi I summation enclosed residues. When you say enclosed residues, it means sum of residues of f of z at all singular points inside C. And let us consider there are n singular points, or you can say isolated singular points inside the closed curve C. And those points are, let us say, where z is equal to z1, z equal to z2, and so on, z equal to zn. And the residue at z equal to z1 we have denoted here by a minus 1 z1. You know a minus 1 is actually called residue, and when you say a minus 1 z1, it means this is residue at the point z equal to z1. A minus 1 z2, what does it mean? It means residue at z equal to z2. And when you say a minus 1 zn, it means residue at z equal to zn. Or in compact form, we can write this expression as integral of f of z along C in anti-clockwise sense equal to 2 pi I summation over j equal to 1 to n a minus 1 zj. In fact, here zj, where j runs from 1 to n, are the enclosed singular points, and a minus 1 zj, as I have told you, that these are the corresponding residues. When you say corresponding residues, it means these are residues at z equal to z1, z equal to z2, z equal to z3, z equal to zn, and so on. So this is the statement. The statement is very simple. We will be actually given such a function that there will be some isolated singular point of this function f of z inside a closed curve C, and closed curve C must be a simple closed curve, and we have to find the residues at those singular points, and then utilizing this result you can find such an integral. So now let us see what the statement says. In this figure you can see that this C is a closed curve of arbitrary shape and size, and I have shown here in this figure this closed curve C is in a complex plane as you are seeing in this figure, and these points where Z is Z1, Z is Z2, Z is Zj here, these are actually the isolated singular points. When you say these are isolated singular points, what does it mean? You have already studied the isolated singularity. It means when we will enclose these points Z1, Z2 and Zj by small circles, taking the points Z1, Z2, so on Zj as center, then these circles will be non-intersecting. They will not intersect one another because the points are isolated singular points. Whenever two circles will intersect one another or cut one another, then those points will be not isolated singular points. So for being isolated singular point, these are non-intersecting circles. Now to prove this theorem, actually we will apply the Cauchy integral theorem for the multiply region. You know, a multiply region becomes a simply connected region when we actually connect the closed curve C with these circles by a crosscut. So see in this figure we have connected the circle, let us say C1, C2 and CJ by a crosscut as you are seeing in this figure, and then you will see we will apply the Cauchy integral theorem and very easily we can prove this theorem. So let us now see its proof. Let C be a simple closed curve in a complex plane. In a complex plane, Z equal to Z1, Z2, so on Zn are n isolated singular points of a function f of z inside C. Remember, these are singular points, and in fact isolated singular points inside the closed curve C. Now taking the points Z1, Z2, so on Zn as centers, draw non-intersecting circles C1, C2, so on Cn and connect these circles to C by cross cuts. We know when these circles will be connected to the closed curve C by cross cuts, then the region inside this closed curve will become a simply connected region. So the region inside C becomes a simply connected region. In fact, originally it was a multiply connected region. Now after connecting the circles with the closed curve C by cross cuts, actually this region becomes a simply connected region. And you know, if it is a simply connected region, then we can apply the Cauchy integral theorem. So we can now apply the Cauchy integral theorem for this region. And what this Cauchy integral theorem actually states, we have seen in previous lectures this theorem in detail, and according to it, when you say according to it, it means according to Cauchy integral theorem. We know that integral along C f of z dz minus integral along C1 f of z dz minus integral along C2 f of z dz and plus so on plus integral along Cn f of z dz equal to 0. Sorry, here there will be in fact minus sign, minus this much, and this equal to 0. You know why we have taken the minus sign here in the terms for the circle C1, C2, C3, so on, Cn. As you can see this figure, when we will traverse along the closed curve C in anti-clockwise sense, then actually these circles C1, C2 and so on Cn are traversed in clockwise sense. So if you will take the plus sign there, then the sense of rotation along these circles will be clockwise. But I have taken the integral in anti-clockwise sense in each term, so the sign becomes negative. And actually we have already studied it in Cauchy integral theorem. So you can see from this result that this may be written as integral along C in anti-clockwise sense f of z dz, this will be actually equal to what? This is integral in anti-clockwise sense along the circle C1 f of z dz plus integral along C2 and in anti-clockwise sense f of z dz plus so on plus integral along Cn f of z dz. So this is our result. Now you have already studied the definition of the residue and the formula to measure it. So we know that the residue of f of z at its isolated singular point is defined as, we have in fact discussed this fact previously. You know, residue is denoted by a minus 1, and this a minus 1 is actually equal to 1 over 2 pi I integral along C f of z dz. In fact, in this expression, C means C1, C2, C3 and so on, Cn. And so from here we can see that the integral in anti-clockwise sense along C f of z dz is equal to 2 pi I into a minus 1. It means 2 pi I into a residue of the function f of z at its singular point. So now utilizing this equation 2, you can see the residue of the function f of z at its different isolated singular points z1, z2, z3 and so on, zn. What will be that? So we can represent actually in this way. So you can say therefore 2 pi I into a minus 1 z1. What does it mean? It means this is residue of f of z at z equal to z1. So you can see z equal to z1 is the residue which is the actually singular point which has been enclosed by the circle C1. So this can be written as integral along C1 f of z dz, and again 2 pi I into residue of f of z at z2. This is written as a minus 1 z2, and this will be actually equal to integral along C2 f of z dz. And in this manner you can write 2 pi I into a minus 1 at z equal to zn. This will be integral along Cn f of z dz. So we have expressed all the integrals in RHS of equation 1 in terms of the residue of function f of z at its isolated singular point. Now we will use this equation 3 in equation 1. So after using this equation 3 in 1, what we will get? So using equation 3 in equation 1, we get what we will get? We will get that integral along C f of z dz. Remember, this C is not particularly a circle. It may be any simple closed curve. So this integral is equal to what? You can see when we will substitute the value of all the integrals in RHS of equation 1, then what will be our result? Actually 2 pi I can be taken as a common factor, and the remaining terms will be a minus 1 z1 plus a minus 2 z2 plus so on plus a minus 1 zn, and these are actually residues at point z1, z2, z3 and so on zn of the function f of z. So, and in compact form you can write this expression as 2 pi I summation j equal to 1 to n, and this is a minus 1 zj, where j runs from 1 to n. And you know this is actually the residue theorem. So the result which I have mentioned in equation A, I am again writing it A, this is the result which was to prove, or you can say this is the statement of the Cauchy integral theorem. So you can see Cauchy residue theorem is now established, and we will use this theorem in the later lectures to evaluate certain types of definite integrals. But till now I am giving you a simple example which is not actually related to the definite integral of real variables, but in general we take a problem to and utilize this theorem to solve that problem, so that your concept of this theorem will be clear. So let us take an example. Using calculus of residues. Calculus of residues, evaluate the integral. Evaluate the integral which is integral along C in anti-clockwise sense 2z minus 1 over z into z plus 1 into z minus 3 dz. This is the problem, and we have to evaluate this integral as the problem says by using the concept of calculus of residues. You can see actually in this problem f of z is equal to what? This is 2z minus 1 over z into z plus 1 into z minus 3, and the simple closed curve C is actually a circle which is defined as, you can see where C is a circle defined as mod of z is equal to 2. When you say C is a circle whose equation is mod of z equal to 2, what does it mean? It means the center of this circle is at z equal to 0 and its radius is 2. This equation shows actually this. So now let us solve this very problem. In fact, to apply the Cauchy residue theorem to evaluate this integral, we will need first of all to find the singular points or the poles of this function f of z, and then we will evaluate the residues at those singular points which are actually inside the circle C. There is no need to find the residue of the function f of z at those singular points which are outside of the closed curve C. So first of all, let us find the poles or the isolated singular point of this function. So in this problem we are given f of z. What is f of z in this problem? This is actually 2z minus 1 over z into z plus 1 into z minus 3. You can see from this figure, from this equation, that we can easily find the poles or the isolated singular point of this function. You know, whenever we have to find the poles or isolated singular point of a given function f of z, we simply equate to 0 the denominator of the function. So to find poles of f of z, we take z into z plus 1 into z minus 3 equal to 0. And you can see from here there will be 3 solutions of this equation. This will be z equal to 0, z equal to minus 1 and z equal to 3. And as the power on each factor in denominator is 1, so actually these are simple poles. So these are simple poles. When you say simple poles, it means these are poles of order 1. So now we will find the residue of the given function f of z at the simple poles which are z equal to 0 and z equal to minus 1, z equal to 3. But before that, we will check, are all these simple poles inside the given closed curve or not? So let us check it. And for checking this, first of all, we will draw our circle and represent these points in that figure. So our circle is mod z is equal to 2. What does it mean? I have told you this represents a circle having center at z equal to 0 and radius equal to 2. So this is the center where z is equal to 0 of this circle. And now you know this is actually the real axis, which I have denoted by x, and this is actually the imaginary axis which will be represented by IY. And you can see all the singular points are in fact real, so all these points will lie on the real axis. First pole is z equal to 0, so this will be actually at the center of the circle. Second is minus 1, and you know this minus radius of this circle is 2, so this point minus 1 will be inside this circle. Let us see, we take here z equal to minus 1. This is the another isolated singular point which is also inside this circle C. But the third simple pole of this function is z equal to 3. As the radius is 2, So definitely this point lies outside of this circle. I am representing it here. You can see in this figure. This is the point z equal to 3. And so you can see that among these 3 isolated singular points, only 2 isolated singular points which are z equal to 0 and z equal to -1 are inside this circle C. So for applying this Cauchy residue theorem, we will need to evaluate the residue of this function at only these 2 singular points, that is z equal to 0 and z equal to -1. There is no need to find the residue at the singular point z equal to 3, which is outside of this circle, because in accordance with the statement of this theorem, the integral of f of z will be equal to 2 pi I times sum of the residues at the isolated singular points which are actually inside the circle C. Since the poles are simple, so we will utilize the formula which we have studied for evaluating the residue for simple poles. So now we can write the residue of f of z at its simple pole z equal to 0. We will use the formula for in case of simple pole. You know, in general this residue is defined as limit z tends to z naught, z tends to z naught, z minus z naught into f of z. This is the formula for evaluating the residue of an analytic function in case of a simple pole. Here actually what is this z naught? Z naught is actually the singular point. So when this singular point will be at z equal to 0, then we will write a minus 1 equal to limit z tending towards 0, z minus z naught. Since z naught is 0, so this will be z minus 0, and f of z. In fact, we are given in this problem, this f of z is what? This is 2z minus 1 over z into z plus 1 into z minus 3. Now you can see this z minus 0 is simply z, so this will cancel out by the z in denominator. So our result is limit z tending towards 0, 2z minus 1 over z plus 1 into z minus 3. Now let us put the limiting value, that is z equal to 0, in this. So what will be our result? This will be 2 into 0 minus 1 over 0 plus 1 into 0 minus 3. So this will be minus 1 over minus 3. And so you can say that residue at the first simple pole z equal to 0 of this function is a minus 1 equal to 1 over 3. So this is the residue at the first simple pole z equal to 0. Now actually we will find in the similar manner the residue of this function at its another singular point which is inside the circle C. And what is that singular point? That is actually z equal to minus 1. So again, a residue of f of z at z equal to -1 is given as. How we will define it? We will again write this is in fact a minus 1. Write here -1. This is for the indication for the singular point, and I am also writing here a minus 1 0. Don't read it at 10. This is a minus 1 0. 0 represents the singular point, and similarly here a minus 1 minus 1. This last minus 1 represents the singular point. So what will be this? Since the pole is simple, so you will again use the same formula. This will be limit z tending towards -1, z minus z0. Here z0 is -1, so this will be z plus 1, minus minus plus. And f of z, you know f of z is what? This is actually 2z minus 1 over z into z plus 1 into z minus 3. So here you can see this z plus 1 will cancel out, and our result is limit z tending towards -1 and 2z minus 1 over z into z minus 3. Now substitute the limiting value of z. So what will be this? This is 2 into -1 over z. Z is -1, so this is -1 into z minus 3. Again z is what? Z is actually -1, so it is -1 minus 3. So you can see this is -2 minus 1, so this will be -3, and here this is -1 into -4, and so this will be 4, and therefore you can see the residue of this function at the point z equal to -1 is equal to what? This is actually equal to -3/4. So these are the residues of function f of z at its two singular points z equal to 0 and z equal to -1, and actually these singular points of f of z are inside the given circle C, which is defined as mod of z equal to 2. But you know, and you can see in this figure that the third singular point, which is actually z equal to 3, is actually outside of this circle, and so there, as I have told you, there is no need to find the singularity, not singularity but residue of this function at this singular point. So I am just mentioning it since the pole z equal to 3 is outside of the given circle C. So there is no need to evaluate a residue of f of z at this pole. Now actually we will apply Cauchy residue theorem to find the value of the given integral. Now applying Cauchy Residue Theorem. Cauchy Residue Theorem. Integral along C 2z minus 1 over z into z plus 1 into z minus 3 dz. What will be this? The theorem states that this will be 2 pi I into sum of the residues at the singular points which are actually inside the circle C, and you know these singularities are A minus 1 0 and A minus 1 at minus 1, and we have already calculated the value of these residues. You can see the first residue A minus 1 at z equal to 0 is what? This is 1 over 3, and the second one is minus 3 over 4. So now you can take the LCM and solve this. So you can see this will be actually equal to what? This will be minus 5 pi over 6 I. So this is the value of this integral. You have seen that very easily we can evaluate such integrals by using the concept of the theorem, Cauchy Residue Theorem, or the concept of calculus of residues. Actually, in further lectures, we will see some particular type of integrals of real variables that can be evaluated by utilizing the idea of the Cauchy integral theorem. So that will be our subject matter in the further lecture.